¿Qué tal? Buenos días. Vamos a empezar. Veamos. Muy bien. ¿Qué tal? Buenos días. Muy bien. A ver, no, creo que ya me escuchas. ¿Ya?
Hola, ¿me escuchas?
Yo sí.
Ya te escucho.
¿No? ¿Nada? A ver,
No.
¿Jesús, me escuchas?
¿Qué onda?
¿Yo? Sí.
Ahí está, Moisés, Jesús me escucha y también respondió. A ver.
Mm,
Porque, por ejemplo, yo si escucho tu micrófono, que lo tienes activado, Moisés. ¿No, Moisés, nada? Bueno, ya se desconectó. Tiene problemas de conexión, yo creo, Moisés, ya. Vamos a esperar un momento a ver si se puede conectar Moisés. Dice que tenía problemas con el audio, ese era el problema que tenía. Entonces, esperamos unos minutos, Jesús, nada más a ver si se puede volver a conectar Moisés.
Ok.
Adelante. A ver, él está conectando, vamos a ver si funciona. Buenos días. Ahí está bien. Bien. Dale, nos vemos. Dale. A ver, Moisés, ahora sí. ¿No? Entonces, Moisés, intenta en el canal de YouTube, pero ten en cuenta de que va algo diferido todo. Bueno, vamos a ver. So let's start now. Well, I want to start with some examples, and then we will later continue with more theory. Okay, so I want to give first some examples of manifolds. We have a couple of them, and as we progress along the way, we will have more examples, and I would like to stress on the examples. So the first one is the sphere. We only work it out for S1. And again, let's think about it the simplest way. So we don't need two charts. We use projection from the North Pole and projection to the South Pole. In that way, we get open sets. Well, we get all of Rn in that case. So this is the example that we have of manifolds. The good thing is that, so at least for each dimension, we have an example of a smooth manifold, which is not an open set in Rn. It's something different. So that's one family of examples. Again, I want to stress the circle, and you will see why. So this is the example that we actually work it out with all the details. And the reason that I taking this one is because in the homework and also in class, we show that if we have two manifolds, the Cartesian product is also a smooth manifold. So for spheres, let's take only S1 and take n copies. So this is what it is called the n torus, okay? The way to think about it, it lives inside R2n, and we have the torus. This is the example that you have seen before. For n equals 2, we usually write it like this, right? This is the torus. But again, you can do it n times, and that will give you an n-dimensional manifold, which is called the torus. And I mean, I took S1 because it has a name. The other example could be S3 times S3 and so on, but that's not a common example. The most well-known example is copies of S1, which is the torus. And now I want to see another class of examples. Some of them, we already know them, and some of them, they will come later on. I'm going to set some notation, and this is going to be n by n matrices with R coefficients, okay? N by n matrices. Now, so define, this is nothing new. This is just Euclidean space. But we have a different arrangement for the matrices, right? N columns, n vectors. But it is the same as a vector in Rn squared. So we know that this is a smooth manifold. So the space of n by n matrices is also a manifold of dimension n squared. Also, we can talk about n by n matrices, but now with coefficients in the complex numbers. In that way, this space is C n squared but we are looking at real dimensional manifolds. So this is R2n squared. Okay, so we have these two manifolds which coincide with Euclidean space. So far, nothing new, just a different name. But I want to single out a few features that first they hold on multivariable calculus, and then they will go on for manifolds. So consider two matrices, Aij and Bij. I'm going to do this only on the reals, but it also works with complex coefficients. So you know very well how is the sum of two matrices is defined. So then I have a function. I take one matrix, another matrix, and the matrix sum to get another n by n matrix. Now, the output or the Aj entry of the output looks like this. Okay, so that's a smooth function. And this is just from multivariable calculus, because the entries of the matrix you get here is a polynomial in the entries of the matrix here and the matrix here. And you know that polynomial functions are smooth functions. So that's a smooth function there. Also holds when you do the scalar multiplication. So now you have a function that goes from R times the set of matrices, and then you get also an n by n matrix. That's also a smooth function. And I want to study another one. So know that all of this is nothing related to manifolds. It is all just multivariable calculus. So now let's talk about the determinant of an A by N matrix. There are several ways to compute the determinant, and I want to use this definition, because that definition is very useful for the things that we are studying. We would like to understand how is the determinant of a function if it's continuous and smooth. So I didn't write it down here, but well, or maybe down, we will see. So here, this is a degree n monomial, and then you have a sign. So the determinant is a polynomial of degree n, and on the Aij entries of the matrix. So again, like in the case of multiplication and sum of matrices, it is just a polynomial function on each entry. Here is only one entry because we have a real number. This is a real number, the determinant. So the determinant, it is a smooth function on all of its domain. So you have a smooth function. Okay, remember this is Euclidean space. You have a real value function on Euclidean space, and it is smooth. It is a degree n polynomial. So again, this is just multivariable calculus. And now I'm going to make a little adjustments. And so all of the knowledge that you know so far about manifolds is going to enter here. Well, in some way. So again, the matrices, you have it here, is Euclidean space. And I'm going to define several subgroups of matrices. The first one, it is the non-singular matrices. This is the general linear group. That's what this is called. That's what GL stands for. So it is the set of all n by n matrices such that A is non-singular. Now, what is another description of a non-singular matrix?
The determinant is not zero.
Right. This is equivalent that the determinant of the matrix is non-zero. Great. Okay, so has sets, this lives in Euclidean space. Okay. But now let's try to understand how is this relation, this subset relation. R2n, it is a topological space. So I would like to know if this set is either open, closed, compact, all of the concepts that you know from point set topology. Okay? Do you have any clue of those properties of this set? Open, closed, bounded. Also, you can ask whether if it's bounded, compact, connected, and so on. You know many properties of topological space, and it is interesting to decide which one of them satisfies GL. So what I claim is that it is an open set. Any idea why it is an open set? So the hint is this. Let's think about the determinant function. Not so much that it is smooth, but it is a continuous function. So you have a continuous function on the set of n by n matrices. What can you say about GL? Jesus already mentioned that non-singular is equivalent to have a non-zero determinant. Then what can you claim from this?
Maybe we can say that the zero is a limit point.
Again, Jesus, the zero
Like,
is
a limit point,
a limit point.
which is not included in the GLN.
Right. So right, you have here the zero, and right, you can have matrices of determinant 1 and then go all the way up to non-zero. They are here, and 0 will be a limit of that. Yes, that's true. But what is most important is that by the characterization that you gave, we have this. Under this function, I take an open set here. The reals minus the 0. That is an open set. The determinant is a continuous function. So the pre-image of an open set is going to be an open set. So this equality holds by the definition. I'm looking only at non-singular matrices, which is the same matrices that such that the determinant is non-zero. So that's the equality, and that's how we get that is an open set. Okay, so this set of matrices is a group, the general linear group, and it is an open set. And now, for what we have seen, if I have an open set in Euclidean space, what is the dimension?
Like the same as the Euclidean space.
Right. So it will be the same as the Euclidean space. In this case, is 2n. Oh, sorry, n squared. Okay, now because you were puzzled by this, you have formulas, the determinant, very explicit things. So decide if this is connected. And if it's bounded. Because we are in Euclidean space with the standard metric, we can ask if that space is bounded or unbounded. Okay, connected and bounded. So now you know that it is open. And now this is something very simple. Once that I told you why it was open, all of you agreed, so it is clear that it is open. And it is very important, this property. We will later on see by the end of the class that it is fundamental, this concept, that the GL is open. Okay, now above, I talked about the sum of matrices, scalar multiplication, but now I'm going to talk about the product of matrices. Here I said a group, but I didn't say what is the operation. So this is a group under the product of matrices. Okay, not under the sum, under the product. So I'm going to consider the product. For the time being, I'm going to restrict to this. It makes sense to talk about the set of all matrices, n by n matrices. But I'm going to take this smallest set, which is GLN. So the product is smooth because what you get here, again, it is a polynomial on the entries of those two. So that's a smooth function because it is a polynomial. each entry is a polynomial function. So that is smooth. Now let's study the inverse function on matrices. Now, in order to talk about this, in this case, I really need to restrict to this one, because precisely non-singular matrices are the ones that are invertible. If a matrix has zero determinant, it will not be invertible, and it doesn't make sense to talk about the inverse map. So I have the inverse of a matrix. So here is very important that I have this. Okay? What formulas do you know to compute the inverse of a matrix? Moises? Jesús?
Yo no me acuerdo de ninguna, la verdad.
¿Perdón?
Yo no me acuerdo de ninguna.
In English?
Yeah, I can remember no one.
Okay, but if I give you a 2 by 2 matrix, can you compute the inverse of a 2 by 2 matrix? I give you a non-singular 2 by 2 matrix, and the problem is to compute the inverse. Will you know how to do it?
I just remember that I have to divide by the determinant, or I can't remember before.
Okay. And well, at least that is important, and that's why we can only talk about the inverse of a non-singular matrix, because you have to divide by the determinant, right? So that's the key point. Okay. There are several formulas for our convenience for the purpose of what we are looking at. I'm going to take this function, right? So the inverse what you guys said, so you have to divide by the determinant, and this is a n by n matrix, and that's the cofactor matrix, la matriz de cofactores. And I think also maybe you have to the transpose of the cofactor matrix. Right? So in order to conclude this, you need to understand this very well. Here, there's nothing wrong. That term is a continuous term, even smooth, because A is non-singular. So you will never have a zero. You will never be dividing by zero, so that's no problem. And here, you need to look what this means, the cofactor matrix. How is it computed? So the cofactor matrix is also will be a polynomial function on the entries of the matrix A. So that will be also a smooth function. There's no problem there. So all of this is a smooth function. The only problem that can arise is here, but we avoid the problem because we have non-singular matrices. Okay, so you have a smooth function there. Now, a more basic question. Remind me the definition of a group. What is a group?
It's a set along what is it? An operation which is has an inverse, it's associative, and an identity element.
Mm-hmm. Right. So of all that you said, in order for that to hold, you need the operation, and for the inverse, you also need the operation, associative, and all the rest. But you need to have those two things: how to multiply and to take inverse of any element. Right? So that's what we have here. So what I'm saying is that the set of non-singular matrices is an example of a Lie group. And here is the definition of a Lie group. It's a group, yes, as you mentioned, you are required to everything holds, all of the axioms, but you need more things that need to fit this concept. The set has to be a smooth manifold. The operation, the product operation has to be smooth. Remember that this makes sense because if Y is a manifold, Y times Y is also a manifold. That was the homework. So it makes sense to talk about this function being smooth and also has to be smooth. So that's the definition of a Lie group. It's a group that at the same time is a manifold such that the product and the inverse are smooth functions. Right? For instance, another example of a Lie group, well, it doesn't even have to be the same. How do you make this into a group? What is the operation that you define there?
Probably with the sum.
Right. So you define the sum of matrices. That's going to be well defined in that set. Remember that we already saw that this is Euclidean space. So this is a manifold. And we saw earlier that the sum of matrices is smooth. The inverse under that operation is just the minus, the scalar multiplication. So this is also an example of a Lie group. Right? It's not as important as GL, but that will also give you an example. Okay, so we will see more, but this is a very important aspect that you must know. Right now, here I want to, it looks very, very basic, but it is very important to understand this when n equals to 1. 1 by 1 matrices with coefficients in R is just R, okay? There's nothing new. And now this open set is this. Okay, let me put it here instead. So GL1 is just R minus the 0, okay? Now, so basically I have just helped you with that homework, at least for n equals to 1. We have a disconnected set and it is unbounded, okay? Great. And I want to put to make this I want to mash up this to the real case and the complex case. Because this is also a very fundamental issue. Okay, now let's see. 1 by 1 matrices with complex coefficients is just the complex numbers. So as a manifold you have R2. Oh, I forgot to put an L here, so sorry. What is GL1 of C?
Like C minus the 0.
Right, exactly. That's correct. Or let's put R2 minus the 0, right? So I have to omit this. Now, so this set is connected or disconnected?
It's connected, right?
I'm sorry?
Connected? I don't know. I was talking about the one below.
Right, right.
That one is disconnected.
This one is disconnected and the other one is connected, right?
Yep.
I mean, at the beginning, it was very boring. It's just the same. R, C. R minus 0, C minus 0. Like the same. But from the point of view of topology, they are very different. One is connected and the other one is disconnected. Okay? And this construct contrast between GL1R and GL1C has important implications in not only in manifolds, but in many aspects of mathematics. Let me just try to put something here. So, okay. I'm going also to help you with the homework. Okay, now, give me an easy example of two matrices here. That one has determinant 1 and the other one has determinant -1.
With any value of n?
Yes.
Oh.
And then a very simple n by n matrix such that the determinant is 1, and another example of an n by n matrix such that the determinant is -1.
One with ones in all the diagonal.
Okay, the other one?
We can make one of those 1 to be -1.
Right. Very good. Okay. So now let's focus in here. So the determinant came here, and the other determinant came here, right? You know that the determinant is a continuous function. Is it possible to find a path in here that goes from the matrix that has determinant 1 to the matrix that has determinant -1?
Not with n equals 1.
Okay. What about the other n's greater than 1? Assume you have a path, a continuous path of matrices that starts at the matrix that determinant 1 and ends at the matrix of determinant -1. Okay? Now, what is the path of the determinant of all those elements in the path? If you compute the determinant, you get a subset in the reals, right? What can you say about that? So you are here, you are here. You have a matrix of determinant like the example you gave, only once on the diagonal, the identity matrix. And you have here another matrix, and that one has determinant -1. Remember that this is in Euclidean space. So assume that you have a path that joins this. So you have an AT there. So I want you to think about this function. Let's assume this is from 0 to 1. What can you tell me about all of this?
Can you repeat the question, please?
Right. So first, the hypothesis. I have a path a smooth path, continuous path of non-singular matrices. At time 0, I'm at A, which is a matrix of determinant 1. At time 1, I am at B, which is a matrix that has determinant -1. Now, I'm going to consider a function that it is defined on 0, 1, on the interval. That function is, at each point, I will take which number, the determinant of that matrix. What can you say about that function?
Well, since it is a path, it is continuous, and the image should be path connected as well.
Right. Right. So
That's kind of a problem.
exactly. So the image of this function has to be a connected set, right? But you know that at time equals 0, you are in 1. And at time equals 1, you are in -1. Because the image has to be connected, that means that the 0 must be in the image. But that cannot happen because you assume that you have a path in GLN. So what is happening is that GLN is not connected. Okay? On one side, you have everything that has positive determinant, and on the other one, everything that has a negative determinant. Right? So you cannot do this. However, well, first, is that clear? Are there any questions?
No, that's fine. That's fine.
And so far, we have only used concepts of topology, okay? Now, let's change this. The example that you gave for A is one in the diagonals, the identity. That matrix is also here, so that's no problem. The example for B was -1 and then only once in the diagonal. That's also here, right? So that's no problem. Now, the same question. Can you have a path of matrices in here that joins A to B? Can you do that? And not only can you do that, I want an explicit example of this. What is the example? Just put the T in the appropriate sense. So the image of the determinant will be something like this, depending what you take. It goes from 1, this is the unit circle, and you get to -1. Right? So again, this set is going to be connected. So this is a very important thing. GLNR is disconnected. GLNC is connected. And the bottom line is a very simple thing. Between 1 and -1, you cannot move in R without passing through 0. But in C, you can avoid 0 and go from one to the other. Okay, so that's with this Lie group, the general linear group. Questions up to this?
No.
Moisés?
Se me hace que va atrasado porque está en YouTube.
Ajá, sí, está, sí, 15 segundos. Lo bien exacto, dice. Okay, so let's move on. I'm going to give you more examples of matrix groups, okay? The difference is going to be that GLN is open, hence a manifold. These examples are no longer open. They live in Euclidean space. So at this point, we cannot say that they are manifolds, but later on, we will show that they are smooth manifolds. Okay, so The special linear groups is the set of matrices such that the determinant is 1. Basically, the S is when this condition appears. Okay, now, for instance, simple question. Is this open or closed?
I think it's close.
Right, because we can take it even here. This is a smooth function. Well, sorry, a continuous function. And I'm taking the pre-image of a point, and a point is closed. The function is continuous, so the pre-image will be closed. Okay, so that's a closed set. And let's move on. Also, in the complex case, here we have the orthogonal group. A times A transpose is the identity. That's ON. And we have the corresponding uncomplex numbers. But we also require the conjugate. We take the matrix, transpose, and conjugate every entry of the matrix. And the product must be the identity matrix. And inside of those, we have these two. Orthogonal matrices whose determinant is 1, and also for the unitary matrices, the special unitary group. Okay, another homework, if you haven't seen this, it is the circle. No, that's wrong. Sorry, this is wrong. O2. And U1. They agree, and they are the circle there. Okay? Right. So all of these will be examples of Lie groups. So far, we only have the set of all matrices and the general linear group, because we all know that those are manifolds. In number 5, all of these, they are Lie groups, but we still need to argue that they are smooth manifolds, and that will come later on. Okay, so now we're going to move to a different subject. Before moving on, are there any questions?
No. So this is just to know that we can do like calculus and matrices.
I'm sorry, come again?
Like these ideas allows us to bring calculus into matrices.
Yes, right.
That's cool.
And you will see that many times, even later on. Calculus of manifolds, and we will use matrices. It's fundamental. Okay, so let's move on now. Remember from last class, we we studied smooth functions, real value functions. We also studied smooth function between manifolds, right? So now we are going to make sense of partial derivatives. Okay, now for this, I'm going to use a convention. It is the same of the book, and it is very useful. So let's think about Rn. Rn, the book makes this convention. The coordinates will be R1 up to Rn, superindex. Now, what is important is to think about this in two ways. It's just the coordinates, but they are also coordinate functions. And that's what I have here. So the Rj is the projection to the J entry. So the Rj's will be the coordinates like X, Y, and Z that we have in R3. But at the same time, they are going to denote functions on Rn. Right? So I just take a point in Rn. And when I apply Rj, I get the J entry, Xj only. So you need to get used to this. It's very useful, this way of thinking about the coordinates in Rn. And again, so roughly, we are like having a parameterization of Rn in some way. That's what we have there. Okay, so now, so far, when we have a manifold, we have used the chart U, phi. And phi is a homeomorphism from the open set in the manifold to some open set in Rn. We have also seen that phi is a smooth function on U, right? But now I'm going to think of phi also in another way, which is very important. And it is this. So phi is going to induce me this function. And that is, so from the manifold, I go to Euclidean space and I project, and that's the definition of this function. Okay? Right, so I have my open set and my map chart. So basically the xj's corresponds, if I have here constant, then I have here the constants, right? So that's what the xj are. So it's like putting coordinates on U. And here you have it. So the xj are defined on the open set U. And so it is also useful to think of a chart this way. Okay? Sometimes I will write a chart like this, and sometimes I will write it like this. And I mean the same thing, the function defined on U that goes to some Euclidean space, a homeomorphism to an open set. Now, what I would like to show to you is that, remember that we have said that this function is smooth, right? But also the coordinate functions are smooth. So this coordinate function is a function on U to R, and it is actually smooth. In order to show that it is smooth, I need to take a chart. I take the same chart, and if I want to know if this is smooth, the definition is I need to know that this is smooth, right? Using the chart. But what is this? By definition, it is this function. By definition of a smooth function. But now I use the definition of xj. Remember xj, how was defined? Right? So the rj's are functioning in Euclidean space and they are smooth. So each coordinate function is smooth. This is smooth. Right? So this is in analogy of what we have said before. Remember that we showed that this is a smooth function, and now we are saying that also the coordinate functions are smooth. Okay, now. With that said, now we are going to make the definition of a partial derivative. So I have a real value function. I have a chart. There it is. And I'm assuming that the function is smooth. And we are going to define the partial derivative of f with respect to the chart. So it will depend on the chart. And it is this. So the definition is missing something. This definition depends on the chart. I forgot to put this. With respect to right? Because if I choose another chart, this will be different, right? So this derivative depends on the chart. So this is what I'm defining. And it is going to be a partial derivative in an open set in Euclidean space. And it is this. Okay? I mean, if you're moving here, then you're moving here. So if you take the partial derivative in this direction in Euclidean space, I want that to be the partial derivative on the manifold along this new path. That's the whole idea of this, right? So this is a smooth function on Euclidean space, and I take the partial derivative in Euclidean space. Okay, makes sense? And sometimes I will write this, and also this notation will be useful later on. Okay, now I just defined the partial derivative and I evaluate it at a point P. So I have a function and I have a point, but the derivative, that number, this is a number. This number depends on the chart. So I can have P fixed, but if I take another chart, maybe the partial derivative will give me a different number. Okay, so in some way that's not so good. But in some sense, we know what number or how that number relates when we take different charts. So let's see this. What I just said, that the value may depend on the chart, except when the value is 0. If I know that all of the partial derivatives are 0 for one chart, then it's going to be 0 for any other chart. That we can say. But in general, this number can be quite different than this number. It will depend on the chart. Okay? And except when all of them vanish. And that's good because you have seen this in calculus. This is a critical point. A critical point is where all of the derivatives vanish. So that will make sense once that we prove this. Okay, now so let's prove. This is what we have. I have a function, a real value function here. I have one chart where all of the derivatives are 0. So now let's take any other chart that contains P, definitely. I'm going to call that V. Phi V is the function and Yj's will be the coordinates. Now, because U and V are in the atlas, I know that this function is smooth. The two charts are compatible. Because they are compatible, so I know that this function is smooth. So here is where the info about the smooth structure enters. Okay, so this is what we know. Is that clear? The partial with respect to the x is 0. And I have the definition there. So now let's compute the partial with respect to the y's. So I want to show that this is 0. First, this is the definition. Okay? Now, I'm going to put here a very convenient identity function. Which is 5u inverse. So that's the identity that I plug in there. Okay? Now, remember that this is a real value function on Euclidean space. This is a derivative in Euclidean space. All of this is a function defined on an open set in Euclidean space, and I'm taking the partial there. So basically, from here on, we are just using multivariable calculus. Okay? Now, I'm going to break this up like this. Why? Because this is what I know. So I use the chain rule of Euclidean space. I have this derivative times this derivative, the chain rule. Now, this I can do because this is this function. And I know that it is smooth. So I can take its derivatives. All of them exist. Right? And now this, I know that it is 0. Hence, that equals to 0. Okay? So this partial is also equals to 0. Any questions? Okay. Now, so this is the proof of this proposition that it says if the partial derivatives of a function vanish at a point, they will vanish with respect to any chart about that point. Okay? So that's good, because remember that the partial derivative depends on the chart. Now, from the proof, I would like to make a statement about this. So this is, we can say, the transition function. I have it here. That goes from the y coordinates to the x coordinates. And I also have the other one, but I will just take that one. Okay, now remember that these are defined on some Euclidean open space. So here I have some open set in Rn, and also here. So this is going to be appear several times because it's the transition. Every time that we have to deal with different charts, those transition functions that go in one direction and the other one, they will have to appear. And you can think of them as a change of variables between the y functions and the x functions. And that change of variables is smooth because the two charts are compatible. Okay, so now that we have proved this, then it makes sense to talk about critical points. And here, I wrote it correctly. I don't need to make any emphasis on any chart. It's just a critical point of the function. I don't care about the chart anymore. But in general, the partial derivatives depend on the chart. For critical points, we are done. Okay, now let's move on with this concept of coordinate functions. Again, this is just like an exercise. If I have a chart, now instead of 5, I'm writing the coordinate functions. Remember that we already saw that xj is a smooth function of u. And then we can ask what is the partial derivative of that function. And it is exactly what you expect. It will be either constant 1 or constant 0. And this is on u. Constant. And I mean, it is a nice exercise, again, only with the idea to have some feeling about this definition that we have seen. Get used to it. Oh. Okay, we already know that the function is smooth. So now we need to compute the partial derivative. And obviously, I'm going to take the same chart because that's what I want here. So I need to consider that chart. And that's the definition of the partial derivative with respect to the chart xi's. And now I use the definition of this. What function is that?
It's the R, right?
Ri. And there you have it. Again, remember that in Euclidean space, the RJs are the coordinates, but also coordinate functions. So we can get either 1 or 0. Okay, so this is a very nice application. And then we're going to look at something else. Any questions? Well, so now we are going just to review the implicit function theorem. No, sorry, first, the inverse function theorem. Yeah, so this is what we're going to do now. And also here, what Jesus mentioned, the concept of the Lie group, GL, will be fundamental here. So let's recall the inverse function theorem, but from R to R only, right? So assume you have a function here. That's the graph of the function. And we assume that it is smooth, right? We assume that it is a smooth function. And what you know from calculus, you know that when the derivative is 0, you have maximum, minimal, or inflection points. So this is when you might have a problem. And here you might have a problem. So at this point, the derivative is 0. I'm assuming that f is smooth. Also here, x1 and x2. Right? Now, if you take any point in between, you know that the derivative is non-zero. And that's what the inverse function theorem tells you. Once that you know that the derivative at one point is non-zero, then in the neighborhood of that point, the function is invertible. Right? That's what you have. So the inverse function theorem will tell you that on a neighborhood of x3, the function is invertible. Okay? Now, let's see a little bit more or less what is going on here. The derivative of a function at a point is a number. But it is better to think of this as a 1 by 1 matrix. And you know this from multivariable calculus, and you have the Jacobian matrix. At one point, you have the Jacobian matrix. So the derivative is a matrix. Okay? So the inverse function theorem on dimension 1 tells you that if the derivative is non-zero, that is, non-zero means GL 1R. Okay? And this is what I have here. Right? So here is where you have the derivative, a 1 by 1 matrix. And the hypothesis of the inverse function theorem is assume that the derivative is non-zero at one point. That means that the derivative is in GL R1. Then what can we say using this? What is happening in points? What can you say about the derivative at points that are nearby x3? What can you say about the derivative? So let's recall this problem. If you have a continuous function that it is non-zero at one point, what can you say about the function, about nearby points? Right? If a function is non-zero in one point and the function is continuous, then nearby points will also be non-zero. Right? And that's because R minus 0 is an open set. If f of x0 lies in an open set, then the points nearby x0 will also lie in that open set. So if the derivative lies here for the point x3, then it's going to lie there for any nearby point of x3. Okay, does it make sense?
Yes. Let me see.
Okay, so that's the conclusion that we can get from this. And well, that more or less is how, when you see this result in calculus, how you prove the inverse function theorem. So the derivatives here will be non-zero, so you will always have injectivity. The failure for injectivity is when you go like this, right? Or the other way around. So that's the failure of injectivity, and at least in that neighborhood, you don't have that, no zero derivative. So you are avoiding this, and also the other way around, like this. So let's do the same in Rn. So we take an open set in Rn and a function to Rn. Let's assume that the function is smooth. So we have n coordinate functions, f1 up to fn. And that's exactly what I said a while ago. For n greater than 1, the derivative is the Jacobian matrix. Right? So for each point of the domain, you have a matrix given by this rule. That function from U to the matrix is going to be continuous. In fact, in this setting, it's going to be smooth, but we don't require that anymore. So I have a smooth function defined on an open set to the set of n by n matrices. Now, if I know that the determinant is non-zero at one point, that means that this matrix lies in GLN. Now, again, this set is open in the set of all n by n matrices. So I have a neighborhood such that for nearby points, all of them will be non-singular. Okay, makes sense? Now, right, and so this is the first part of the inverse function theorem on Euclidean space. This is what you already know. And we have a similar version in the setting of manifolds. Oh, well, right. Now, the other thing that I wanted to mention is this. And that's why I wrote it also this way. Because once that you have this, if this function is locally invertible, that means that on a subset W, f is locally invertible. So you can also think that as a chart, that will give you a chart. It will be a homeomorphism to its image. In this notation, to its image only. Not on all of you, but on a smaller set, the inverse function theorem will give you a chart. Oh, sorry. Okay, so this is, I'm assuming something that you know from multivariable calculus. And for a smooth manifold, we also have the inverse function theorem. So I have a smooth manifold of dimension n and a function like this, right? Again, I write the function, the coordinate functions, n of them. And this is the inverse function theorem, but now for manifolds. So I need to rely on a chart. I need a chart to talk about the partial derivatives that we know on several variables. So I need a chart to make sense of this. So if I know that at one chart the determinant is non-zero at one point, then this function is going to be a diffeomorphism. On a smaller set, locally is a diffeomorphism, right? And again, that will also give you a chart. Okay, so I'm not going to prove this result, but this is what the analogous in manifolds of the inverse function theorem that you know from functions from in one variable and n variables. So the whole idea is the determinant of the Jacobian matrix in non-zero at one point, then nearby the function is invertible. The reason being that the determinant of nearby points is also going to be non-zero. So it requires to have a one-point constraint. You have it in nearby points. The reason being that the non-singular matrices is an open set. So it suffices to have one point and you have a whole neighborhood of them. So the basic idea comes from R1, so to speak, you avoid the points where the derivative is 0. And there you will have an inverse. Great. Okay, so with this, we end the class. Are there any questions or comments?
No, not from me.
Okay, now let me just again emphasize on this. Using the inverse function theorem is another way to define a smooth manifold. So remember that it means that in a small neighborhood of P naught, you have a homeomorphism, and that will give you a chart. And I think we will see later on example we will invoke the inverse function theorem to define manifolds. Okay, so if there are no questions, we will continue tomorrow. For tomorrow, I would like also, I don't know if I will cover the implicit function theorem, but because what I want to do tomorrow is to define another manifold. I would like to show that RPN is a smooth manifold. The only thing is that we will show that this is a manifold using that it is an abstract topological space, not using that it lies in some Euclidean space. We will not use that. So we will rely only on the sense that it is a nice topological space. So this is one of the aims, to have, again, examples of manifolds. And then example of smooth functions, critical points. Great. So the time is up.
RP is the projective?
Yes, the real projective space of n dimensions. You have RPN and also CPN. But both of them, they are studied similarly, at least that they are manifolds, in the same argument. And maybe we will only see RPN. Great, so for tomorrow, the real projective space is a smooth manifold of dimension n. Done? Okay, so
All right.
see you tomorrow then. Good luck.
See you tomorrow. Let's see.